So we finished up section 3.3. We're not doing anything else in chapter 3 because it's just not stuff we cover in this class. So now we're going to look at section 4.1. 4.1 is on what we call rational functions. Now, yesterday we looked at things like this, like x cubed plus 3x squared minus 2x plus 6. That's called a polynomial. Specifically, this is a cubic polynomial because the highest exponent is a 3. Well, today we're going to look at what's called a rational function. A rational function is when you take a polynomial and then you just divide it by another polynomial. That's rational. So a rational function is one that you can write as a fraction, where the top and the bottom are both polynomials. There's only one restriction on the bottom, and this is the same restriction on any fraction. But what is in the bottom cannot equal what? What can you never put in the bottom? Yeah? Zero. So the polynomial that's in the bottom cannot be 0. And at first you might think, well, wait, can a polynomial just equal a number? Sure. If you have f of x equals 3, that's called a constant polynomial. It has no variables in it. So yes, polynomials can just be as simple as a number. They can be as complicated as having things cubed and squared and that stuff too. But that's called a rational function. It's when you take a polynomial and divide by another. There's another example of a rational function. What do we call a polynomial where the highest exponent is a 2? What kind of polynomial is that? Yep, that's a quadratic. So when the highest exponent is a 2, that's a quadratic. How about when the highest exponent is a 1? What is it? Linear. So this is a rational function where you're taking a quadratic and dividing by something linear. So we've got an example there. Here's another example of a rational function. I mean, you don't have to write them all down. I'm just showing you examples. This is a quadratic divided by another quadratic. Different examples of rational functions. So one thing we're going to look at now is how do you find the domain of a rational function? Well, I already mentioned this, but what's the one thing you are not allowed to do when you have something that's rational? When you have a fraction. You can't put a 0 in the denominator. So the domain of a rational function is every number that doesn't make the denominator 0. You can use anything you want that doesn't make the denominator 0. So we'll take one of those examples that I had on the previous page, and we'll find the domain. So the example here says x squared plus 1 divided by x minus 3. What number, or if you think there's more than one, tell me numbers, but what do you think you cannot use for x in that case? Right?
-3.
Well, if you did -3 minus 3, that would give you -6.
Oh, 3 then.
3. 3 minus 3 is 0. So the domain is everything except 3. Everything except 3. This is what that would look like as a picture. Here's 3. You can't use 3. You can use anything you want that's lower. You can use anything you want that's higher. You just can't use 3. So this is how you write it. Think of that left arrow as part 1. That's part 2. So the domain here is in 2 parts. Everything below 3 and everything above 3. And this is how you write it. For the part that goes below 3, how far down does it go below 3? Forever. It just keeps going. So it goes from negative infinity up to, not including the number 3. That's why we put a parenthesis on it. Now part 2. That starts at 3. And how high does that part go? Infinity. Not including infinity, because you can't reach infinity. Not including the 3, because you're not allowed to use the 3. And when your domain is split into 2 pieces, you put that symbol between the 2. That symbol means or. It means or. So you can either pick a number from below negative 3 or above 3. Bless you. But the domain is everything except positive 3. Okay, let's look at this one. Part B. So Cameron, can you remind me again, what are we not allowed to do in the denominator?
Any number that, or put x that makes the denominator equal 0.
Right, we can't let the denominator equal 0. This one's a little harder to see what would make it 0. But we talked about something yesterday that you can do to this that makes the zeros easier to see. What could we do to the denominator that would make the zeros easier to see? Let's say you wanted to set this denominator equal to 0 and solve it. Could use quadratic formula, but there's an easier way you can find what makes the bottom 0. Yep?
Would you cross out like terms?
Can you do what?
You cross out like terms.
If you had like terms, you'd have to have something like this. And in that case, I would say you should combine the like terms. But we don't have any like terms to combine here. So yeah, factor it. Factor the bottom so you can easily see what would make it 0. And Alex, what's going to be my first term in each parenthesis when I factor it? Yep, I'm going to have an x and an x. Next, I need my signs. So, Kiana, what would my signs be? To factor that. Yep, we're going to need a positive and a negative. Now I need 2 numbers, Austin, that multiply to give me 2.
1 and 2.
1 and 2, I would suggest trying them in that order. Let's see what happens. X squared minus 2x plus 1. Well, minus 2 plus 1 gave me negative 1. I want positive 1. So I guess that order didn't work.
So you just flip one?
Just flip the signs. Let's try it now. X times 2 is 2x. X times negative 1 is negative 1x. 2 and negative 1 gives me positive 1. That's good. So now, what two numbers can you not use because they would make the denominator 0? Yep. 1 and negative 2. So think of that one like this. Here's negative 2. Here's positive 1. You can't use negative 2, and you can't use positive 1. So you can pick anything below negative 2. You can pick anything between them, or you can pick anything above 1. How many pieces does this domain have? The last one had 2. This one has 3. How would you describe all the numbers below negative 2? How would we write that? So we want to write it like we did up above as an integral. How would we write everything below negative 2? Yeah?
You put not the bracket, but the parentheses.
Yeah.
With the negative infinity.
Yeah.
And then negative 2.
Okay, there's the first part. That's everything below negative 2. Or, Tyler, how would I describe everything between negative 2 and 1?
I did brackets.
Well, bracket means you can include it.
So then maybe it's just the regular parentheses.
We just want to use the parenthesis because we don't want to include it.
So it's just the negative 2 and the negative 1 then?
Yep. Or everything above 1, not including the 1. So don't put a bracket on the 1. Putting a bracket on it means you can use it. If you use it, we're going to divide by 0. So that is your domain. And here, that was your domain. Yep.
Why is the middle one negative 1?
Whoops. Let's see. Thank you. Positive 1. If you accidentally did something like that on a test and I had this separated into 3 parts, you'd get credit for the first one and the last one, but I wouldn't have given you credit for the middle because you had the wrong side. Yeah. But yes, it should be a positive. Any questions on that? Yeah. Yeah. So I've shown you guys a couple different rational functions. Okay, I showed you that one there. We had another one there that was a little more complicated. Well, now I'm going to show you the simplest one. That's the simplest rational function you can have. 1 over x. It's just a number in the top, just a single letter in the bottom. No powers, nothing. Now, what number are you not allowed to plug in for x here? 0. So when you get close to 0, watch what happens when you draw it. Watch when the graph goes towards 0, all of a sudden, it curved very quickly. And that's a little misleading because it actually looks like the blue graph stops. This keeps going up. That keeps going down. And that's what the graph looks like. This is the graph of 1 over x. So we just graphed it. Now I want to ask you a question. As x approaches infinity, so in other words, as x gets bigger and bigger and bigger and bigger, I want you to look at this graph and tell me which way is infinity first, to the right or to the left?
Oh,
Well, one of them's infinity, one of them's negative infinity.
right.
So infinity, positive infinity is to the right. What is this graph getting closer and closer to, but it's never actually going to reach it as x gets bigger and bigger? It's going to get very close to 0. Why won't it ever reach 0? Well, look at this. If you take 1 and divide by 50, do you get 0? You get something small, but it's not 0. How about 1 over 1,000? No. 1 over 1,000,000? It's not 0. 1 divided by anything is never 0. You can get closer and closer and closer and closer the bigger you make this number. So as you head to the right, you are approaching a value of 0. How about if you head to the left? Like what if you let x be negative 100, or negative 1,000, or negative 1,000,000? What are you getting closer and closer and closer to? Oh, Chris?
0.
Yeah, you're getting closer and closer to 0 when you head to the left as well. The difference is when you go left, you're coming up to 0. On the right, you're coming down to 0. But either way, you're getting closer and closer and closer to 0, but you never touch it. The way we would show that you never touch 0 would be to take a line like that and make that a little thinner. And put a dotted line right in there. So you never actually reach it. Does anybody know what this line is called? It's a line that you get closer to, but you never reach. It begins with an A. A what? It's called an asymptote. Yes. So as you head right and left on this graph, this particular graph, you got very close to 0. Is it always going to be 0? No. It depends on what your graph is. But if you get closer and closer and closer to a number as you go left and right, that number is called a horizontal asymptote. And for this particular graph, it is at the number 0. So to find a horizontal asymptote, take your graph and imagine you could just keep traveling to the right forever. And ask yourself, as I do that, what am I getting closer to? So an asymptote is just a thing you get close to, but you never reach it. It's kind of like if you were looking at your test average, and let's say you got a 90 in the first test. If you got a 90 on the first test, could your test average ever be a 100? No. It's not possible to get 100 because you've already got a 90. I don't care how many hundreds. You can average 50 hundreds with a 90. It might be like 99.999 or something. But it's never going to be 100. It'll just get close to it. All right, so let's see. So let's look at this one. I want to find the horizontal asymptote. All right. 1 divided by x plus 2. So to find the horizontal asymptote, in your head, let x get bigger and bigger and bigger as a positive number, or think of it getting smaller and smaller and smaller. Negative 1,000,000, negative 10 million. And think about what would happen if you plugged that in to the formula. Yeah? Yes. So focus on the part that has an x in it. As x gets bigger and bigger and bigger and bigger and bigger in this problem, I want to know what will happen to the whole thing. But first, just focus on what happens to what's in this box. As x gets bigger and bigger and bigger and bigger, what happens to the thing in this box? Yeah?
It gets smaller and smaller.
It gets smaller and smaller and smaller, and eventually it gets pretty close to what?
2. I would say
this box gets very close to 0. Right? If x is 1,000, you'd have 1 1,000. If x is 1,000,000, you'd have 1 1,000,000. That's very, very small, but it's not 0. Now, if you take something that's extremely small, basically approaching 0, and you add 2, what number do you basically get? 2. Right? This graph is getting closer and closer and closer to the number 2. The bigger you let x be, the closer and closer you're going to get to the number 2. When you write a horizontal asymptote, you always write y equals. If you put x equals, we're going to talk about that in a minute. That's something else. But y equals is what you want for horizontal. All right, let's look at this one. 1 divided by x minus 3. So just focus on what's in that box first. As x gets bigger and bigger, what's going to happen to what's in that box? That what's in that box is going to keep getting closer and closer to 0. The bigger you make x, the closer you get to 0. And if you take something close to 0 and subtract 3 from it, what do you basically get? Negative 3. And what letter do we want to put? Y equals negative 3. Now, what if I made this top number a 12? Would anything change? Anything, Tom? No. Because pretend x was a really huge number, like 1 billion. Well, whether you divide 1 by 1 billion or you divide 12 by 1 billion, it's basically the same. It's still extremely small. It's still getting closer and closer to 0. The only thing that affects a horizontal asymptote is when you add or subtract a number outside of this box in red. That's what affects it. All right, so now let's take a look. There's not a ton in this section. Let's, I guess I can take a second. I'll graph one of the ones we just did. Let's do the first. 1 over x plus 2. Okay, if I draw that, 1 over x, put it in parentheses. 1 divided by x, close it, plus 2. And let's put a line where we think the horizontal asymptote is. So there's the graph of 1 over x plus 2. That red line is the horizontal asymptote. And does it look like the horizontal asymptote is correct?
Yeah.
Yeah, it's good. Of course, the thinner you make it, better it looks. But that's fine. So yep, that's how you graph it. And if you graph the other problem, 1 over x minus 3, well, or what do we do? 1 over x and then the minus 3, it would look like it moved down 3 instead of up. That's all. Did I change my window?
Yeah.
Nope, I left it out of the standard window. But it is important that you put that 1 over x in parentheses.
Yeah, I did. It's just a straight line.
And you did a zoom 6?
Alright, there you go.
Oh, did it work?
Yeah.
Okay. Okay, now I want to look at something else. We've already looked at what happens to this graph if you head to the right forever and you head to the left forever. It's called a horizontal asymptote. Now I want to look at what happens as we head towards the middle. Specifically in this graph, I want to look at what happens as we head towards 0. Let's pretend like we are traveling this way on the graph. What starts to happen as we head towards 0 following those red arrows, what happens to my y value? It gets bigger. How big? Infinitely big. As I start to get closer and closer and closer to 0, keep heading towards it, keep going, keep going, keep going, keep going, all of a sudden, the graph goes straight up and it heads towards infinity. Now, let's look at what happens as we head towards 0 again, but this time this is called from the negative side. As we come towards 0 from the negative numbers, what happens to my y value? It starts to what? It starts to go down to negative infinity. If you start coming at a number, and all of a sudden your graph curves up on one side and down on the other, that's what we call a vertical asymptote. Okay, we're going to write that down. So this part you guys just told me. As you approach 0 from the positive side, positive means from the right. As you approach it from the right, your y value increases without any limit. In other words, it goes straight up to infinity. And this is how you write that sentence. Okay, symbol for symbol, this means as x approaches the number 0 from the positive side, the y value goes up to infinity. And I'm not going to write the whole thing out as a sentence again, but I will write it with symbols. As x approaches 0 from the left side, that's what negative means, from the left. So go back to the picture. As we come at 0 from the left, all of a sudden, the y value approaches negative infinity. It goes down forever. So this kind of behavior that I just described, that is called a vertical asymptote. It's something you get closer and closer and closer to, just like horizontal. But this one is vertical. Looking back at our picture, we would do something like this. That's how you would show a vertical asymptote. Should make it a little better. So, how do you figure out the vertical asymptotes? The horizontal asymptotes are when you head to the right and to the left forever. You let x get a really, really, really big positive or negative number. Well, the vertical asymptote, in the problem we just did, right here, was basically that vertical line right there. What value are you not allowed to use in the denominator here? 0. That is your vertical asymptote. The vertical asymptote are the values that make the denominator 0. Visually, it's when you approach a number from the left and the right, and all of a sudden, it curves up or it curves down. When you write the equation of a vertical asymptote, that's how you write it. It's not y equals, that's horizontal. This is x equals. Now, I basically said that you look for where the denominator is 0. But there's one thing you have to be careful. The numerator and denominator cannot have a common factor. So what do I mean by that? In that problem, the numerator and the denominator have a common factor, x minus 2. If I asked you what the domain is, I would say it is all numbers except 2 and negative 3. You can't use either one of those numbers. But the only one that has a vertical asymptote in this problem is negative 3. Because you have a common factor between these two, what's going to happen if you draw something like that is you get a hole in your graph. It's a very, very, very small hole. You can't see it on the calculator. But let me draw it, and I'll show you what it looks like. So x minus 2 divided by x minus 2 and x plus 3. All right, so negative, can't use 2, and you can't use negative 3, but you're only going to see a vertical asymptote at negative 3. Watch. And somebody who walked in here and looked at that right now, they would probably say, oh yeah, looks like there's an asymptote at negative 3. Well, that's from this. You can't see the hole in the graph at 2. If you wanted to draw this correctly, what you should do is erase this little blue part and put a circle like that. So it should look something like this. And then continue on. There is a hole in the graph at 2. And, if you don't believe me, go to the table and try typing in the number 2 and look at what you get. Error. You can't type 2 into this graph because it causes you to divide by 0. It's just not an asymptote. You can't type in negative 3 either. Those are the two numbers you can't type in, but only one of them gave you an asymptote. So, any questions on what I mean by common factor, numerator and denominator? And how would you know if you have a common factor? Well, you factor it, and then you look at it. If they match up, no asymptote. If you change this to a different number, well, if you type that in now, you would see 2 vertical asymptotes in this problem. Positive 2 and negative 3. There's no common factor here anymore. They're all different. So just try to put in, make that a minus 4. You're going to see 2 spots where you could put vertical lines. There's 1. There's 2. So you have 2 separate vertical asymptotes. And that breaks your graph into 3 separate pieces. All right, let's try this one. Okay, find the vertical asymptote. When we want to write the equation of something that is vertical, how does the equation always start? X equals, yep. Y equals is for horizontal, this is x equals. And what number would you not be allowed to use in the denominator? Yep, 2. There's your answer. Vertical asymptote is at x equals 2. How about this one? 1 over x plus 3 minus 1. Yeah.
So the one on the outside of that, would that be the horizontal?
Yeah, this has to do with horizontal. This has nothing to do with this problem, this minus 1. So x equals minus 3. So what if I do this? It's still x equals minus 3. This number changes the horizontal. This number changes the vertical. They're totally separate. And while we're doing that, because then this is the last thing. we're not going to graph that one because I've graphed enough of them to show you. So skip that. Okay, let's try this one. Don't have to do the second part. All I want to do is describe the horizontal and the vertical asymptotes. If you look back at every problem we've done so far, look at what has been in the top. It hasn't been 2x minus 13. What was in the top in this problem? 1. How about what was in the top in this one? 1. What was in the top in this one? 1. This one? 1. It's always been a 1. That's how you always want it to be when you're trying to describe horizontal and vertical asymptotes, if you can. You really don't want to have an x here. You could have a number other than 1. You could have a 2 or a 3. That wouldn't really matter. But what you don't want is an x up here. So the only way we can fix this, so we can describe these two things, I think you could describe that one right now. Just look at what we make the denominator 0. That's pretty easy. But the horizontal is a little trickier. Because the horizontal, you're looking for plus or minus a number at the end. We don't have a number there. So we need to fix it, so we do. So let's take and divide x minus 5 into 2x minus 13, just like we learned yesterday. Let's divide this out and see what we got. So take x minus 5 and divide it into 2x minus 13. Now, remember one way I showed you can write your answer when you do this problem. Quotient plus your remainder over your divisor. Or you could think of it this way, same thing. Remainder over divisor plus quotient. The point is, when you rewrite it, the quotient is going to be that number that's normally at the end. It's going to be the negative 12 in this problem. That's going to be the quotient. So that's the number we need to find. All right, so let's divide it out. Divide x into 2x. What's 2x divided by x? Yep. 2. That's basically all I need. But let's finish it off. 2 times x. 2 times negative 5 is negative 10. And 1. What do I do with those columns?
Subtract them.
Oh, sorry. Tony. Yeah, sorry. Subtract them. Yeah. So 2x minus 2x is gone. Negative 13 minus 10. That's like negative 13 plus 10, which is how much? Negative 3. Here's your quotient. Here's your remainder. Write it just like that. Remainder over my divisor plus my quotient. There we go. So now we should be able to easily see the horizontal. You checked back in and then you're fine. Yeah.
What's that?
You're fine.
Was I not supposed to scan the bathroom twice?
No, that's just when you're leaving.
Oh.
Yeah, when you come back, I know where you're going. You're going right there. So you're good. So quotient, that was the whole key. So let's start with the vertical. What's the vertical asymptote in this case? What is it? 5. X equals 5. And now, what's my horizontal, which we couldn't really tell at first? Yep.
2.
Yeah, 2. Because think about what would happen to what's inside that box if x gets bigger and bigger and bigger and bigger. You would divide negative 3 by something that's getting bigger and bigger. Basically, it would approach 0. Plus 2. And what letter do we use for horizontal?
Y.
1. There you go. So sometimes you have to do the long division. That's why I taught you long division yesterday, to get the horizontal and vertical asymptote. Okay, any questions before we look at the last thing? Last slide. So we looked at a mixture problem yesterday. That type of mixture problem, I think we did. Did we do mixture yesterday? No. Maybe we did it. Yeah, it might have been before yesterday. Might have been last week. Because I teach this class 4 different times and everyone's at a different spot. So this type of mixture problem is a lot easier than the type we did before. So let me just start by asking that question. If you had 50 ounces of liquid sitting in front of you, and I told you that out of the 50 ounces in that container, 35% of it was acid. The rest of it's water. How would you figure out how many ounces of acid are in that container? If there's a total of 50, and I'm telling you 35% of what you're looking at is acid. Yep.
I divide 50 by 100% and times it by 35%.
Okay, so yeah, you basically divide by 100, so that would turn this into 0.35, and then you could just multiply it by 50. So it's the same thing that Sam just said. So if you had 50 ounces and 35% of it was actually acid, that means you take 50 times 0.35 and you get 17.5. Same idea if I said to you, you had a 50-question quiz and you got 35% of the questions correct on the quiz. How many questions did you get right? You got 17 and you got half credit for another question. Same idea. Okay, so what we're going to look at in the last example is called it's a concentration problem. So keep this fraction in mind. This is how you find concentration. You take the amount that's actually acid, and you divide by the total. So, if I had 25 ounces of acid, and I had a total of 100, then I would say that the concentration is 25%. 25 out of the 100 ounces are acid. So keep that in mind, because that's going to be how we do this problem. It's the same numbers we had up above. You have 50 ounces of liquid sitting in front of you, and 35% of that is acid. So out of the 50 ounces, 35% of it is acid. What we're going to do is we're going to pour 100% pure acid into our mixture. So what we're doing is we're making our mixture stronger. It's 35%. We want to make it higher. So we're going to take something that's pure acid and pour it in. How many ounces are we going to pour in to the 50? X ounces. So I want to find a formula for the new concentration. So remember the formula that I just gave you. Amount of acid over the total. Well, first of all, you're starting with something that already has acid in it. So let's start with that. We have 50 ounces, and 35% of it is acid. So Jenna, how much acid do we already have?
50.
So 50 is the total amount of liquid, and 35% of that is acid. So what's 35% of 50? 0.5. So we already have in terms of the amount of acid, we already have 17.5. Plus, how many ounces of acid are we adding in? We're adding in how much? X. When we're done, that's how much acid we will have. What we started with plus what we added. Now the bottom is the total. How many ounces of liquid are we starting with in total? Starting with, Aisha? Starting with 50. And how much liquid are we adding to it? Yep. It's X. Now we're starting with 50 and we're pouring in X liters of acid. That is our new concentration. So let's graph it and see what it looks like. When you graph it, use parentheses. 17.5 plus X divided by 50 plus X. Now, question. If I don't pour anything in and I leave the solution the way it is, what's the lowest concentration of acid that I will have if I don't touch it? Yeah?
35%.
It's not going to go below 35%. So on the y-axis, we are not going to go below 0.35. What's the highest my concentration could approach, but it will never reach it? If I just keep pouring in pure acid, just keep dumping it in, yeah?
99%.
Yeah, you could get just under 100. So as a decimal, that's 1. So the concentration is going to be a decimal between 0.35 and 1, but it'll never reach 1. X is the amount of acid we add, so negative 10 doesn't make sense. How much acid are we adding? Well, I don't know. Let's just say we add maybe up to 150. There's your concentration of acid going up higher and higher and higher, but leveling off at 1. It'll never reach it. Okay, so there's your graph. And the last part says, how much acid should we pour in so we get a 75% mixture? So we're going to use the calculator. What do you think I would have to type in Y2 to put a line at 75%? Yeah?
0.75.
Yeah, 0.75. Now the answer to that question is right in front of us. I have a mark on my graph exactly where the concentration hits 0.75. So what do you think I need to calculate? Yep. Yep. Calculate where they intersect. So second calc, intersect. And there you go. If you add 80 ounces, you will make the mixture exactly 75% acid. You don't have to worry about solving that by hand, just on the calculator. So that's section 4.1. The rest of the week, we're going to focus on section 4.2 okay, for the whole rest of the week. So that's the homework for tonight. Okay, just make sure you copy down 3 through 7 and 11 to 23. Those are odds. And question 48, I think it has 3 or 4 parts to it. You just have to do part A and B. And we'll go over that tomorrow.